Okay, hey everyone, let's get started with the third example review. Okay, is it good? Yeah, so this will be the last example review for you guys. And yeah, hopefully it gives you a final example so you can figure out what you need to do and everything. So we're going to review this paper here. It's called the Reach Profiler, and it proposes a new methodology for profiling for DRAM retention errors. And this work was done by our group, so myself and Jeremy, who's a PhD student in our lab as well, under Professor Mutlu, and it was presented in ISCA in 2017. Okay. So I'm going to start off with the summary and technical content. But I'd like to mention the technical content is organized more like a conference talk. But if you pay attention, you'll see that these sections in the conference talk pretty much map one-to-one to the sections that you need to show in your presentation, right? So we have like problem, goal, motivation, key idea. All of those will be there. They might just not be under that exact name, right? And so this was the title slide. So I'm going to start off with a summary of this work, right? And so the high-level motivation for this work is that DRAM refresh actually incurs a significant performance and energy overhead in today's systems. And we have ways to sort of get around this, but we need to be able to identify exactly where the DRAM retention errors are in order to manage them. And so the specific problem we focus on in this work is that DRAM retention failure profiling is actually very hard. It's complicated by cells that change their retention times dynamically, and the current profiling methods that exist are actually either unreliable or they're just too slow. And therefore, our goals in this work are twofold. First, we want to thoroughly analyze the trade-offs surrounding retention failure profiling. And second, we want to use what we learned to develop a fast and reliable profiling mechanism. And to this end, we make two key contributions in this work. First, we perform the first detailed characterization of LPDDR4 DRAM devices, and we use what we learned from that study to propose reach profiling, whose key idea is to profile at either a longer refresh interval or at a higher temperature than the target operating conditions. And this is because that's where cells are more likely to fail. Through our evaluations, we find that reach profiling gives us a significant performance and reliability improvement over prior works, and it actually enables longer refresh intervals that were previously unreasonable due to profiling overhead. Okay. So I'm going to start off with some background on DRAM refresh, right? So DRAM inherently encodes data using leaky capacitors, right? So here's a graphic of like a simplified DRAM cell. And so we have a capacitor which encodes data using either the charged or discharged state. And we have an access transistor which is used to read from or write to the cell, right? And so one thing to note is that there's several charge leakage paths by which charge can enter or exit this capacitor, right? And the important thing is that the stored data in the capacitor can actually be corrupted if too much charge leakage occurs. And this is the same thing as saying if the capacitor voltage degrades too far. So here's a simplified diagram of what the cell voltage might look like over time. And we see that it degrades in a sort of exponential characteristic, right? So on the y-axis we have a capacitor voltage, and on the x-axis we have time. So we can define a voltage level along the y-axis called Vmin, below which we can no longer tell what data was originally stored in this cell because it's degraded too far. Right, so as long as the voltage in the cell stays above Vmin, we call this a retention success because we know what's in the cell. Unfortunately, if it's below Vmin, we call it a retention failure because we can't tell anymore. And so we can also define a point on the x-axis at the crossover point, which is called the retention time. And the retention time essentially defines how long a cell can hold its value. So we have to keep in mind that DRAM is actually much more than just one cell. And in fact, there's actually hundreds of billions of cells in a typical DRAM device. Any one of these cells can experience a retention failure, right? And so just as a specific example, an 8 GB DRAM device contains 64 billion cells, right? And again, all of these can experience failure. And so to this end, we use a process called DRAM refresh. And DRAM refresh periodically restores the leaked charge in every single cell in the DRAM device, right? And so for our typical DDR3, DDR4 devices, this is every 64 milliseconds. So essentially every 64 milliseconds, we refresh every cell in the entire device. And as you can imagine, this results in significant system performance and energy overhead. Right, so here's some data taken from our evaluations. And so on the y-axis, we show the average system performance overhead. And on the x-axis, we show several different DRAM chip sizes. And we see that as the chip size increases, the performance overhead of refresh increases quite a bit. And it becomes extremely significant by the time we're on larger chip sizes, such that we expect today and moving in the near future. So what we want to do is we want to somehow decrease this refresh overhead, right? And so it turns out that we can actually do this. Most cells actually don't need such a short refresh interval, and they actually won't fail if we extend the refresh interval a little bit. So here's some data that comes from our experimental analysis. And so on the y-axis, we show the number of failing cells in this device, and note that it's a log axis. And on the x-axis, we show different refresh intervals, right? So on the very left, we have the default refresh interval of 64 milliseconds. And you see that there's no failures whatsoever. And this is expected because that's the normal operating point. However, as we begin extending the refresh interval, we get more and more cell failures, right? And because it's a log axis, these small changes are relatively significant, right? So if we just focus on the left-hand side of this plot, we see that for very modest increases in the refresh interval, we actually have very few failures, less than 100. And given that a DRAM device has hundreds of billions of cells, this is not too many. And we actually have ways to manage these failing cells. And so this leads us into retention failure mitigation. And so the prior work actually has many different ways of mitigating these errors once they occur, right? So 100 errors occurring here and there, these mechanisms can mostly handle that type of situation. However, all of these mitigation mechanisms and others that aren't listed here have one thing in common. They all assume that they can perfectly identify the set of failing cells that need to be handled, right? And this is where the problem occurs, because we need a fast and reliable profiling mechanism to find this set of retention failures, and only then can these mitigation mechanisms do their work, right? So now I'm going to talk about some of the challenges surrounding retention failure profiling and hopefully convince you that it's a relatively difficult problem. So here's a picture of an idealized DRAM refresh operation. So we have a number of cells shown in green and some I/O logic that's typical of a DRAM device. And then we have a refresh counter which counts down 64 milliseconds until the next refresh operation is necessary. So if I go ahead and animate this, we'll see that the voltage in each of these cells decreases, but every 64 milliseconds, the refresh operation restores this charge such that every cell capacitor is fully charged, right? So now this is a very idealized picture of the refresh operation because all of these cells essentially have identical retention times, right? And this means that the same short refresh interval of 64 milliseconds is perfect for all these cells. However, in reality, real DRAM cells exhibit significant variation between different cells. And so let's take a look at why this might happen. So I'll itemize some of the sources of retention time variation between cells, right? The first is process voltage and temperature. And so the retention time of different cells varies at manufacturing time due to process variation and at runtime due to voltage and temperature fluctuations, which are typical of pretty much any semiconductor device. A second point is that there's a phenomenon called data pattern dependence, which means that the retention time of any given cell actually changes depending on the data that we program into the cell and into the neighboring cells, right? And so if we program this DRAM device with all ones, we expect the cells to have different retention time than if we program them all with zeros. Right? And finally, there's an effect called variable retention time, which leads to random and unpredictable variations in the retention time. And this occurs due to several various circuit level leakage phenomena. But the problem for us is that this is unpredictable, and so these cells will be changing retention times all throughout DRAM operation. So now let's take a look at a more realistic picture of a refresh operation. So here we have cells with heterogeneous retention times. And I show cells with a short retention time in red and those with a long retention time in green. And as we see, as time goes on, the voltage in the cells with the short retention time degrades much faster than the cells with the long retention time, right? And so this means that the cells with the short retention time require a short refresh interval in order to ensure correct operation, whereas the cells with the long retention time can handle a longer refresh interval. Right? So if we put this back together into our original picture, but this time we extend the refresh interval to 128 milliseconds, which is double the default, right? We actually find that the cells which are shown in red with the short refresh interval degrade voltage so far that they experience retention failures, right? And so the problem that we want to solve in this work is how can we quickly and reliably determine the set of failing cells at any given increased refresh interval t, right? That would be the ideal problem. And so now I'm going to talk about some of the current approaches to retention failure profiling. And keep in mind this is current as per the time this work was published, right? So in 2017. So the first solution I'm going to talk about is called ECC-Scrubbing. And the key idea of ECC-Scrubbing is to leverage error correction codes by periodically accessing all of these ECC words in order to continuously detect any new failures that occur. And so the pros of this approach are it's very simple because it just requires read accesses to all of the different DRAM locations. And the error correction hardware will just tell us where the errors are, right? So it almost comes for free. We just have to issue these read accesses. It's also low overhead for the same reason, because while we're doing the scrubbing operation, issuing all of our read accesses, DRAM is still available for normal operation, right? Albeit with some contention with these scrubbing requests. The cons of this approach, however, are that it's unreliable. And this is because in between scrubbing operations, it doesn't account for any changes in data pattern or any other changes in retention time that might occur. And this means that this approach can potentially miss failures that occur between scrub operations, right? The second solution that we consider is sort of the state-of-the-art solution, and it's we just call it brute force profiling, right? And so the key idea is that for n different data patterns over m different testing rounds, we first write a given data pattern to DRAM, then we weight the refresh interval we want to operate with, and then we check for errors, right? It's very straightforward. And the approach here is to test all these different data patterns in order to get around this data pattern dependence effect, right? And so a lot of the prior works sort of assume this type of profiling mechanism when they're presenting their mitigation mechanisms. And assuming this works, you can identify the set of bad cells, and then you can go handle them with your mitigation mechanism, right? So the pros of this approach are that it's much more reliable because it finds a much higher percentage of all possible failures using all these different data patterns and the different testing rounds. Unfortunately, it's very slow because you require many different testing rounds to get high reliability. And this means it's also pretty high overhead, right? Because while we're doing this type of operation, a DRAM is not available for normal operation, right? And so, DRAM is unavailable for a long time while we're doing our profiling phase. Therefore, our goals in our work are to first study the different trade-offs surrounding retention failure profiling, and then develop a fast and reliable profiling mechanism to get around these issues. So now I'm going to talk a little bit about the characterization studies that we did with real devices, right? And so our experimental apparatus allowed us to test a whole bunch of LPDDR4 devices, which were state-of-the-art at the time this work was published. And we have devices from across 3 major manufacturers. And in order to isolate these temperature variation effects, we do all of our testing in a temperature-controlled chamber, right, which can test within a certain range and has some tolerance. So here's a list of some of the studies that we did. We studied the effects of temperature, data pattern dependence, and so forth. And we actually found that the first 3 studies on this list, the temperature, data pattern dependence, and retention time distributions, showed results that were very similar to prior work with older generation devices. So DDR3 devices and so forth. And so I'm not going to focus on them in this talk. Instead, I'm going to focus on the bottom 2, variable retention time and individual cell characterization, because these show new results that help motivate our profiling mechanism. So the first study is on variable retention time, and we approach this by showing a long-term continuous profiling study, right? So here this plot shows some data taken from a representative device at a fixed refresh interval of 2048 milliseconds, which is considerably higher than the default of 64, right? So we expect errors. On the y-axis here, we show the number of new failing cells that appear throughout our profiling steps over the x-axis, which shows time. And this is in days, so this is over about a week of data collection, right? And so what we see is that at first, a whole bunch of errors appear, right? And on this log axis, you're over 10 to the 2. So we get plenty of errors each time we run the profiling routine. But eventually, after about half a day to a day, this settles out into what we call the steady state accumulation regime, where there's a sort of constant number of errors that keep being discovered over time, right? And it's very low, you have like in the tens regime of errors that you're discovering. And so what we observe from this is that new failing cells continue to appear over time. And we can actually attribute this to the variable retention time effect. Because what's happening here is that we initially discover a set of bad cells, but there are other cells that will fail at a later point in time that aren't failing right now, that we'll discover as time goes on, right? And the variable retention time effect means that cells are changing their retention time. And it's one possible way to explain this data that we've observed. So essentially this means that the set of failing cells is changing over time, and so it's not good enough to just run profiling once and then call it quits and be like, oh, here's our profile, we're good now, right? And what we take away from this analysis is that 2 things, right? Both error correction codes and online profiling are actually necessary in order to manage these new failing cells that continue to appear. Error correction codes because in between our profiling steps, some errors will occur, and we can't constantly be profiling, right? And so error correction codes will help manage those failures that appear in between. And online profiling because at some point there'll be so many new errors that occurred that we need to profile again and get the currently updated set of errors, right? The second analysis that we did is we studied the failure probabilities of individual cells. Right, so here I'm showing a cartoon of an idealized cell and what its retention time might look like. So on the y-axis we have the probability of a read failure to this given cell, and on the x-axis we have different refresh intervals we might be running with. Right, and so we say that this idealized cell has a retention time of 3 seconds because below 3 seconds the cell never fails, but above 3 seconds the cell always fails. Right, and so this is idealized because a real cell doesn't fail quite so exactly. Instead, we find that it follows a normal distribution in failing. And what this means is that even though we ascribe it a retention time of 3 seconds, potentially at the mean of this distribution, there's a non-zero probability of failure below this retention time. And above this retention time, it's a continuous distribution, right? So there's always a non-zero probability that the cell might fail. So now I'm going to show some data taken from a real device, and this data was taken by repeatedly sampling a given cell for a period of time, right? And so here we see what sort of looks like the normal distribution characteristic, though as it's real data with a finite sample points, it's not perfectly smooth. But essentially we sampled each of these points 16 times, and we observed the number of times it happened to fail, right? So here it failed 9 times out of 16, and so the probability of failure is just slightly over 50%. And so here now I show 8 different cells from the same device. And it's a little easier to think about it if I apply their normal distribution fits, right? So I go ahead and do that. And so now we have these cells that the failure probabilities over different refresh intervals, right? So let's say we want to operate at a refresh interval of 1.7 seconds, which is considerably higher than the default of 64 milliseconds. And therefore, it significantly reduces the amount of refreshing we need to do. And therefore, it reduces the performance overhead of refresh significantly. So here we'll observe that there are many cells that happen to fail, right? And we actually have 6 cells that fail with a non-negligible probability of failure. But the problem is that down here, these 2 cells are pretty hard to find because their probability of failure is so low, right? We'd have to sample these cells, on average, I guess around, 8 times just to figure out that they're potentially failing cells. And so instead, we see that if we profile at an increased refresh interval, these same 6 cells become much easier to find, right? Because under these conditions, these cells are much more likely to fail. And the lowest probability of failure is, over 0.75, right? Which is makes profiling much, much easier. A downside, however, is that we'll observe some other cells to fail at this increased refresh interval that don't fail at the refresh interval we actually want to operate at. And so we call these false positives, right? And so potentially we can tolerate a certain amount of these. And so the observation we make is that any given cell is more likely to fail at a longer refresh interval or at a higher temperature, right? And this leads us into the key idea of reach profiling. And so reach profiling is based on the key idea that profiling at a longer refresh interval and or a higher temperature actually allows us to find the cells much more easily. And so here's a simple graphic showing, we can either increase the refresh interval or temperature. And I didn't show the error distributions for temperature, but in our paper we describe how it has a similar effect as increasing the refresh interval. So the pros of this approach are that it's much faster and much more reliable, right? Because reach profiling is searching for cells where they are most likely to fail. On the downside, we might discover some false positives because the profiler might find cells to fail during profiling that aren't actually going to fail during normal operation. Right, so we can think of this as a sort of complex trade-off space here, right? We have temperature on one dimension, refresh interval on the other, and some target that we want to operate our device at. And so the questions we sort of need to ask are, do we need to profile here? How far do we need to go? Do we actually, if we go up, increase the temperature, increase the refresh interval, the profiling will be faster, more reliable, but we get false positives. Instead, we could go in the opposite direction, right? What will happen here is profiling will be slower, it'll be potentially less reliable, but we'll have far fewer false positives, right? And we could potentially move anywhere in this space to do our profiling. And so if we want to really turn this into a concrete methodology, we have to ask some questions, right? And so we come up with 3 key questions we need to ask. The first is, what are desirable profiling conditions at which we should profile, given a particular set of target conditions that we want to operate at? Second, how often should the system be profiling? And third, what information does the profiler need in order to make all of these decisions, right? And so in order to do this analysis, we identified 3 key metrics that are useful for categorizing any type of profiling mechanism. The first is runtime, which is essentially how long does profiling take. The second is coverage, which represents what proportion of all possible failures are actually discovered by the retention failure profiling mechanism. And the third is false positives, right? Which is how many cells do we observe to fail during profiling, but that don't ever actually fail during normal operation. And so we explore these 3 metrics across many different profiling conditions, many different devices and so forth, and we try and understand the trade-off space here in order to answer our 3 questions. So the first question that we wanted to answer was, what are the desirable profiling conditions? And what we observe is a little bit surprising. We find that there's very similar trends across different devices and different manufacturers. And we find that as a general rule, in order to maintain 99% coverage of the set of errors, we find that we can get a 2.5x speed up by profiling at plus 250 milliseconds above the target refresh interval, sort of regardless of what that target refresh interval is, at least for reasonably low error rates. And this comes at an approximately 50% false positive rate. And while that might sound high, if we only have 100 errors to begin with, you're moving 100 to 150, and many of these error mitigation mechanisms can easily handle that type of error rate. And we can actually push the speed up even further, over 3.5x, by profiling at even more aggressive refresh intervals, say 500 milliseconds plus, but that comes at the cost of increasing false positive rates, right? And so if these false positives are tolerable, then maybe this is not an issue. There are many more examples of this and detail in the paper. We show distributions of all of these values so you can get some intuition for yourself. And if you're interested, you can go take a look at that. The second question we want to answer is how often should we be profiling? And we actually estimate this using a probabilistic model for error rates that are tolerable in practice, right? And so we use our empirical data to feed into this probabilistic model and generate estimates for real devices. And it's a little bit complicated, so I don't want to go into it here, but the details are in the paper of how we actually do this. And as a specific example, just for your point of view, if we need to reprofile every 2.3 days for the configuration shown here, right? And this is a pretty aggressive increase in the refresh interval from 64 to 1024 milliseconds, right? And maintaining 99% coverage of errors. The final question we want to answer is, what is the necessary information in order to make all these decisions? And this is important because the profiler will need to have access to this in order to decide how to use this best. And so we find there's two key pieces of information. The first is the cost of handling the identified errors. And it's sort of abstract because it depends on the particular error mitigation mechanism you're using, right? So let's say you're using error correction codes. If we have one error within a code word, which might be 64 bits long, say, it's no big deal, right? Because it's just hidden and the error correction mechanism will fix it. However, if we have two errors in the ECC word, it'll manifest as an uncorrectable error, and that'll be a big problem for us. On the other hand, there's many different papers that propose fancier mechanisms. For example, there's a paper called REAPER, which hopefully one of us will present later on during the semester. This paper proposes bucketing different regions of DRAM into different, essentially different buckets that can be refreshed at different refresh rates. And so all you're doing by having false positives is just moving regions of DRAM from one bucket into another. And if you're not doing too much of that, maybe it's not a big deal at all, right? And so knowing the error mitigation mechanism, we can sort of identify the cost of handling those errors. The second piece of information we need to know is some sort of empirical per-chip characterization data. And we need this in order to reliably estimate all these profiling parameters that I mentioned before, right? How much should we increase the refresh interval? How much should we worry about temperature? All of these. And the details of how much data we actually need are in the paper. And ideally, the manufacturers would provide this kind of data to us when they give us the device. If not, it's not too complicated, and we could sort of run an extra profiling phase, a one-time profiling phase to figure this out for ourselves. Okay, so finally, I want to talk about our end-to-end evaluation and show some of the performance and energy results. So we evaluate what we call REAPER, which is actually our simple implementation of reach profiling. And so REAPER makes a number of pessimistic assumptions. First, it assumes that the entire system pauses when profiling needs to happen. And this is very pessimistic because it's essentially saying that whatever is doing the profiling, say some firmware in the memory controller, gets exclusive access to DRAM. And any applications that need to access DRAM are just excluded from the DRAM until profiling is completed. The second thing we assume is that the REAPER only manipulates the refresh interval, but not temperature. And we believe this is a reasonable assumption for devices in the field, because controlling temperature, unless you have some lab set up and apparatus, it might be a difficult thing to do. Whereas the refresh interval can be controlled potentially just by programming things in the memory controller. So our evaluation methodology is through simulation. We simulate performance using a simulator called Ramulator, and we evaluate energy using a tool called DRAM power. Our configuration is, a pretty typical 4-core system with 8 megabytes of last level cache, and we have DRAM that essentially mirrors exactly what we studied in an experiment. In terms of workloads, we also use the SPEC 2006 benchmark suite, which is the same one that the memory channel partitioning paper used earlier, and we create 4-core benchmark mixes by drawing random samples from the benchmark suite. So here are the key performance results, right? So this is one slide sort of summarizing them all, and it's a little bit complicated, so I'll go through it bit by bit. So on the y-axis, we're showing end-to-end system performance gain, right? And on the x-axis, we show different refresh intervals. And these are all increased relative to the default of 64 milliseconds. For each of these different refresh intervals, we're showing 3 box plots. And it's a box plot because it's showing the distribution of performances across all the workloads we evaluated. So there's 3 box plots for each of these refresh intervals. The leftmost one is the previous best profiling mechanism, which was brute force profiling. The central one represents our mechanism, REAPER, and the rightmost one represents the ideal profiling mechanism, which suffers no performance overheads from having to profile. And so what's happening here is that we're seeing a lot of performance benefits from increasing the refresh interval because we don't have to issue so many refresh operations. However, as we keep going, the benefits degrade because we start having so many errors that we need to profile more and more often. So if I first direct your attention to the left side of this plot, with a modest increase in the refresh interval, say doubling it to 128 milliseconds, we don't actually have to reprofile very often because there's not that many errors in the first place. And so the profiling overhead is not very high. And we see that both brute force profiling and REAPER maintain a significant amount of the benefit of the ideal profiling mechanism. On the opposite extreme, at a very high refresh interval, we have so many errors that we're constantly profiling, and this adds so much overhead that we actually get negative performance gains, right? The performance suffers significantly. If instead we focus on some regime in the middle, say a refresh interval of 1024 or 1280 milliseconds, we see that both mechanisms manage to get some sort of performance benefit, but it begins diminishing. And in both of these cases, reach profiling maintains much more of the ideal profiling benefit than the previous best profiling mechanism is able to. And so through our evaluations, we find that on average, REAPER enables 16.3% performance improvement at a significant power reduction for refresh intervals within this range. And the takeaway from this analysis is that REAPER actually enables longer refresh intervals, which are unreasonable with the profiling overhead of brute force profiling. And it's a step towards increasing the refresh interval even more than is possible with the baseline mechanism. So the paper contains a lot more analyses that I didn't go into in detail here. For example, we have a lot more of the characterization data and a lot more details about the trade-off space characterization. And we also go into detail about the probabilistic models for tolerable error rates, and we also present detailed results on our evaluation, including power results, which I didn't present here. And so I want to end the technical analysis with a summary of what happened and what this paper is about, right? And so again, I'm going to recap. The high-level motivation for this work is that the DRAM refresh performance and energy penalty is very high for modern devices. And the problem that we focus on is that retention error profiling is very hard, right? And so the goals of this work were to analyze the trade-offs in profiling and then develop a good profiling mechanism based on what we learn. And that's exactly what we do. We perform the first detailed characterization of many different LPDDR4 devices, and we use that to propose the reach profiler. And through our evaluations, we find that the reach profiler achieves a significant profiling speed up at a power consumption improvement, and it actually enables longer refresh intervals that are unreasonable with previous approaches. Okay, so that concludes the technical section. And as I said, these aren't the exact same section headings as what was in the other examples in the paper, but these sections that I presented sort of map to exactly what you need in your talk, right? And so this is one more free-form way that you could potentially structure your talk if you wanted to do so. So now I'm going to move into the analysis, right? And so I'm going to start off with the strengths that I identify in this work. So the first strength that I have is that this paper tackles a difficult and important problem. And I hope through talking about the challenges of profiling that I've convinced you that there's a lot of effects here that are very probabilistic and hard to manage. And that makes this a difficult problem to fully solve, right? Because we can talk about having, say, 99% coverage of errors or 99.9, but it's very difficult to say 100% coverage because these retention times are changing all the time, right? And so what's true for a single instant in time is not true always, right? And this is why we need online profiling and to continuously do this. And inherently, it's a high overhead process, right? And so by amortizing it over all of runtime, it can provide a good trade-off point, which was what I was trying to show in the performance results. Another strength is that the key idea of this paper is very intuitive, right? We profile for errors where they're most likely to occur. That's pretty much it, and I think it's pretty easy to understand, right? And so in our characterization analysis, we found a way to make those errors more likely, and that allows us to use this to develop a profiling mechanism around that. Another strength is that this work enables many error mitigation mechanisms that themselves rely on a good profiling mechanism. And so the impact of this work is not limited to just improving profiling. It also extends to enabling these error mitigation mechanisms, of which there are many in the literature, and many that you could probably come up with if you gave this enough thought, right? And so it's sort of a more far-reaching idea than just the problem that it solves by itself. Another strength I'd like to highlight is that reach profiling is a pretty effective solution because, as the evaluations show, it improves performance and reliability over the previous best solution. And this is not to say that it fully solves the problem or anything like that, but it does take a good step forward from the previous best mechanism. And finally, it's the first paper to present a lot of system-level characterization data with these LPDDR4 devices. And while that might not seem like the biggest thing, it's actually a pretty important point to note, because having these error rates and these error distributions, the trade-off space characterization, having this published in the literature allows anybody else who looks at this paper to sort of take these error rates and things and compare them with other devices, right? Both going past into older DRAM devices, seeing what the error rate trends are, and looking forward to future devices to try and project what the issues will be with error rates going forward, right? And so the data itself is a good contribution. Okay, so now I'd like to talk about some of the weaknesses of this work. And so the first weakness I identify is that REAPER needs hardware modifications for profiling, at least as presented in this work, right? And so the way it's presented in the paper is that we need to add some sort of firmware in the memory controller to execute this profiling routine. And if you recall, we give this firmware exclusive access to DRAM, right? So while this firmware is executing, nothing else may touch DRAM, right? And this is necessary for several reasons. First, in today's devices, when we try and modify the refresh interval, we don't have full freedom to modify it for arbitrary parts of the DRAM. We can only modify it at the granularity of a rank. And a rank, if you remember, is the level right below a channel. And so it's a huge region of DRAM, right? And so we have to change the refresh interval for this entire region at once, or not at all, right? And so when we're profiling, we have to somehow I guess save that data that's already written there, and then we need to do our profiling, and then we need to copy the data back. It's a very extensive process, and it requires some sort of hardware support. If we have some sort of system where this programmability is just exposed to, I guess, the system software, then maybe this is no longer necessary. But as it stands right now, there are only a few processors that freely allow you to program this refresh interval value to whatever you need it to be. And so for those systems, it might be much easier to implement. And many others don't allow you to do this. And so this hardware support is a weakness and a limitation of this work. Another weakness is that REAPER requires the ability to modify refresh timings and temperature in the first place. Right? So as I just said, not all CPUs will allow you to change the refresh interval. And if you can't change that, then you essentially can't apply this profiling methodology, right? Similarly with temperature. So let's say I'm trying to profile my laptop here. Short of having like a hairdryer and a fan blowing on it, there's no real way I can manipulate the temperature at will, right? And so then I can be passive about it and try and profile based on what the passive temperature changes are, or I can try and run some really intense code and heat up my machine or something like this. Yeah, so this is another limitation of the work. Another weakness in general is that profiling is still expensive, right? So the key idea of this sort of REAPER-like approach with online profiling is to infrequently run very expensive profiling jobs, right? And this requires, as I said earlier, data migration, right? We have to save this data to disk, run our profiling, write data patterns, and then copy it all back. And this is all very expensive. It could take several minutes of profiling. And it's not too big a deal at low error rates because it's amortized, right, over total system execution. But that doesn't, it's still like each individual profiling phase is very expensive. And so that's a weakness of the work. Another weakness I identify is that this approach is inherently probabilistic. It's not guaranteed to identify every bit, right? And as I said earlier, these cells are changing retention times, and there's many effects that can cause that to happen. So it's very hard to not be probabilistic about it and make some guarantee. It's not even clear to me if there is a way to have it not be probabilistic, but it is how this profiling mechanism works, and so that's another weakness. And finally, as always, we can complain about the evaluation, right? So I think the evaluation here has several limitations. The first is that it does not account for DRAM idle time. And this is important because the characteristics of how the DRAM error patterns will look during idle will actually be quite different from during normal operation. Right? Because during normal operation, you're accessing the device, changing the data patterns, introducing a lot of circuit level noise to the device, which will cause the retention times to change much more dramatically than if the device is just sitting there idle, right? And similarly, for the power measurements, for the power evaluation that I showed earlier, we showed that this has significant power benefits. However, if the DRAM is constantly idle, it's hardly burning any power at all. And so the power overhead will be significantly more. The second thing to talk about is the generic spec benchmarks. And this is the same argument I made with the memory channel partitioning paper, right? Where is this profiling mechanism best suited for? And if it's not fully general purpose, why are we using a general purpose benchmark suite, right? And so we can sort of always talk about that, but that's sort of a common weakness. The third thing is that it does not incorporate the overheads of real error mitigation mechanisms. And this one's a little bit more subtle, right? Because in the performance analysis I showed before, we showed the ideal profiling mechanism that suffers no overhead from profiling, but at no point did I show the performance overheads of the mitigation mechanism itself. Right, so for example, if we go back to that radar example I gave, we're refreshing different regions of DRAM with different refresh rates, right? There's some cost to that. We have to do some lookup to see what should be the right refresh interval for this region of DRAM, and I have to do some sort of analysis to figure out which regions of DRAMs fall where. All of this comes at additional overhead, and that overhead is not encoded in this performance analysis that we did here. And it's partly because that analysis would be different for every error mitigation mechanism that you might consider. And there's tens of them in the literature, so are you going to evaluate all of them? Also, we're trying to show the most generic case here, right? This is your sort of upper bound benefits. And by implementing a specific error mitigation mechanism, you'll lose whatever performance power that mitigation mechanism costs. And finally, I want to mention that reliability is analyzed analytically rather than demonstrated through experiment. And I didn't talk about this too much in the talk, but essentially we have this analytical model, right? This probabilistic model for showing how the error rate transforms with different refresh intervals, and saying, can we tolerate this error rate, or is this just too high? Depending on a particular ECC strength, is this going to be okay? And we didn't actually demonstrate this through experiment. And again, it's a trade-off, right? Is the analytical model sufficient to basically show that this would work, or do we need to go show this on a real system, spend a lot of time, implementation effort, just to show the same thing we could potentially show through these analytical models? But it's not evaluated through experiment, and therefore it's, again, a weakness of the work, right? So next I want to talk about some of my thoughts and ideas, and again I'm going to focus on extensions to this work, right? So the first thing I want to talk about is maybe we can identify these weak cells faster by doing more intelligent things, right? And so two things that came to mind were, first, we can manipulate other DRAM access characteristics. So one good example is this data pattern, right? So as I showed with the brute force profiling and with this REAPER mechanism, we test a set of data patterns, right? And ideally, these will give us a good idea of what is the worst case. But it's not necessarily the worst case pattern, right? And so if we can do something more intelligent with the data patterns and potentially figure out some intelligent algorithm to figure out what the worst case is, we could find these weak cells much faster because they'll fail much more quickly. Similarly with timings, right? So I talked a lot about changing the refresh interval. This is just one timing for the DRAM device. There's many other operating timings, and they all have different error mechanisms that will come into play. And maybe some of these error mechanisms will have something in common with retention errors, and we can identify these errors much faster. Another potential approach is combining this REAPER approach with a different profiling mechanism, right? So one good example is ECC-Scrubbing. So the way REAPER works is we propose doing this heavy-handed profiling phase, then we profile again at some later point in time, but in between we rely on error correction to handle any errors that occur. Instead, what we could do is we could maybe use ECC-Scrubbing in between these two profiling phases. And what that would do is continuously collect the errors that continue to accrue, and we could maybe push these two profiling phases farther apart. And the net result would be a much more efficient mechanism than either of these just by itself. The second idea I want to mention is that we can maybe improve the performance costs of REAPER by being much more intelligent about this data migration. Right, so as presented in the paper, when the profiling occurs, essentially everything is dumped to disk, profiling happens, and then it's read back from disk, right, which is a terrible way to do things. We could probably do this a lot more intelligently, right, because there's probably whole areas of memory that aren't even allocated. So there's no point dumping any of that data, right, because it's just garbage data. Also, we can potentially be migrating this data all the time, right? So when it comes time for profiling, the rank that we're going to profile, we could have been slowly moving data out. Assuming there's extra bandwidth available during runtime, this cost is basically amortized over the normal runtime, right? And so we won't be paying that penalty anymore. And the net result will be the profiling phase itself will be much faster and much more efficient. Another potential direction is to implement fine-grained refresh commands. And some really older generation DRAM devices actually did have something like this. In today's devices, the refresh is a very highly optimized process, and you have a very limited control over it, which is why you can only refresh like a rank or at best like a bank at a time. But if in research, we're free to propose whatever we want to propose, right? And so if we propose some sort of intelligent mechanism to have a more fine-grained refresh command, we can start profiling small pieces of the DRAM at a time, as opposed to just having to do everything in one shot. The third thing I want to mention is that it's always possible to do this, right? Demonstrate this mechanism on a real system, because the paper didn't do that. And as I was saying for memory channel partitioning, right? Maybe when we implement this on a real system, we'll get some new insights, right? What we thought was going to happen doesn't actually happen, or the trade-off space is a little bit different than we thought it would be. And especially at the system level here, right? So we're going to require some system support. Either this firmware that executes, it could be as simple as a state machine in the memory controller, in which case you just tell it to go. Or it could be something more complicated, right? We could have like an operating system thread that's in charge of this profiling, and its kernel thread spins up, does some profiling, and then spins down when it needs to. There's lots of approaches, and so implementing on a real system has a different set of challenges than just simulating it. Okay, so finally I want to go over some of the key takeaways that I think are the important parts of this work, right? So first, I want to mention that retention failures are more likely at increased temperatures and refresh intervals. And this came from studying the failure probabilities of individual cells, right? And so this is an important contribution of this work. Second, we find that with reach profiling, the key idea is that we're going to profile at these aggressive conditions where the failures are more likely to occur. But we find that this improves not only profiling speed, but also reliability. And doing both of those at the same time is a great win, right? Because usually it's a trade-off between one or the other. Next, online profiling is necessary to deal with these VRT errors. And so this observation has actually been made in the past with some other works. This work serves to reinforce that, especially with these new devices that we've been testing. And this is an important takeaway because it's basically saying that this problem is much more complicated than just coming up with some really fancy algorithm, right? We need to do this profiling over and over because these cells keep changing. And maybe there's some way to do that. And maybe there's better ways than we propose here, right? One more thing I want to mention is that, so this type of work uses insights from real devices to implement some new mechanism. And in this case, to implement reach profiling, right? And this is a very interesting solution because we come up with some sort of scientific observation based on our studies, and then we use that to do some engineering work and actually implement a new solution. And so it's a very neat process, let's say. And finally, as I mentioned earlier, the impact of this type of work goes beyond just solving the narrow problem that it focuses on. So we focus on retention failure profiling, which could be viewed as a very specific problem. But if we have a good profiling mechanism, we can do much more with it, right? So it serves to enable all of these other papers that have error mitigation mechanisms, or those that want to study the error characteristics, so on and so forth. Okay. So now the last part, I want to open up for some general questions and discussion. And so I have 2 slides worth of these. And so the first question I have is, how else can we potentially improve profiling speed and coverage? And if not, if there's no way we can think of to do this, how can we better tolerate the overheads of profiling, either as presented here or maybe something else that you might be able to come up with? Do any of you guys have any ideas to this effect? Go for it.
In your possible improvements, you talked about lower granularity in the profiling, or at least in the data migration.
Yes.
That could maybe even be extended. Like on general purpose machines, usually not all of the DRAM is used at once. Mm-hmm. So the profiling could happen just on one bank or so on a lower granularity. So it could continuously profile some part of the memory.
I see. So are you saying maybe, just to rephrase maybe so I understand better, so maybe if the system is only using a small portion of the memory, then you could profile what's not in use and then keep moving this data around maybe or something like that, and so that way the profiling overhead is sort of overlapped with normal operation entirely. Yeah, something like that. That makes a lot of sense. It's possible. So then you incur the overhead of moving this data around, or at least when you're going to profile these small regions, you have to do it, but you're doing it much less often at smaller granularities. Yeah. I guess you could imagine that also being tied in with the so for example, in the memory channel partitioning paper, we have the operating system support for mapping data intelligently. Here could also be the case, right? If we're going to launch a new process, only map the data when you know that this piece of memory has already been profiled, because otherwise you'll have to move it anyway, right? Or something like that. Yeah, I think that's a very good point. Yeah.
And also you wouldn't have to write all this stuff back to disk.
Yeah, you wouldn't have to write it back to disk. You just move it memory to memory, right? Even use a proclone, right? So yeah. Yeah, I think all of these are different approaches to consider, and obviously they have their own trade-offs, but yeah, it's very good. So anything else about these two? No, fair. So the next questions I have are, so for what type of systems do you think this type of periodic profiling is okay? Right, so we have all sorts of types of systems, right? Let's say this is, my phone. Do I want it to go down for 2 minutes every hour because it needs the profile? It's probably unacceptable. But for, let's say a data center situation in the cloud or something, there's already lots of people sharing this machine, and you can easily migrate jobs between machines. Maybe there's a way to tolerate this much more easily, right? So, yeah, can you guys think of any systems where this is okay or not okay? And yeah, why it's not okay for those cases? Go for it.
I think it becomes more okay the bigger or the more distributed the system is. Although I think it also heavily depends on high of a workload this system has, because with high workload there's less chance that you can offset the work to some other node if you want to profile the other node.
Yeah, that's fair.
So generally, larger systems will be more tolerant.
I actually think that mobile systems are also not affected much because they have a lot of downtime. So a phone, maybe has a long time of 4 hours, and then you're using it quite a bit, and it could just randomly, when it knows you're not going to use it much at 3 or 4 a.m., do the profiling.
That's a very good point. Yeah, go for it.
Or if you have like more than one RAM stick, you could just do the profiling on one RAM stick, and in the meanwhile use the other for general usage. And then when one is done with the profiling, then just do it on the other one. So just not all at once.
Yeah, not the whole system going down at the same time, right? Yeah, I guess that ties right back in with like ways to do this a little more intelligently. Yeah, sounds good. That makes sense. So sort of as a follow-up to that question, and so how might this affect the workloads we're studying? Now, this has been a theme throughout, and I think it will continue throughout the rest of the semester too, right? So yeah, these standardized benchmark suites, but if we know that, say, we're going to do this during phone downtime, right? Or we're going to do this in large systems where we can easily manipulate the data. What type of workloads do you think are most suitable for that, right? Do you think it makes sense to just take a sample of those types of devices, figure out what people run mostly, and then evaluate with that, show that in the paper? Or do you think it's better to show this general workload and be like, oh, this is representative of pretty much everything, so you can get a good idea of what's happening? Like, what do you guys think about that? Like, what would you rather see in the paper when people are evaluating things?
You should probably show both, right? One we do nothing with the RAM, and one we really blast them with max.
Yeah, so
utilization, and then see what happens.
That's right. So it's not even like real workloads at that point. It's like cases that represent what will happen in reality, kind of. Yeah, fair enough. I'm sorry, were you going to say something?
Isn't that one of the rat holes?
It is. Yes, that's exactly the right question. Yeah, or statement rather. Yes, it is. It is a rat hole. I think it doesn't make sense to go too far into this, but the reality is when you do present this kind of work, you do have to figure out what you're going to show, right? And so you can't show everything clearly, right? And so, but you do need to decide what's best to show. And in this case, we made the trade-off that, okay, we're just going to show this generic benchmark suite and hope that that's good. But if we do want to target this proposal towards one specific area, like if we're going to pitch this as, oh, this is best for data center workloads, then maybe it is best to evaluate that kind of thing. And so I didn't mean to make the discussion spiral down into this rat hole. But I think it's just good to think about it and keep that in mind. Yeah, go for it.
I have a question on these spec workloads. What kind of workloads do these entail? Like, are these like all over the spectrum?
Yeah.
Just like
no, that's fair. I think they try to be, right? The goal of the benchmark suite is to sort of be representative of what a person might run on like a computer, right? So there's like, for example, it consists of a bunch of different applications, right? One is like extracting a file from some compression algorithm, right? Like a zip file or something. Another one is like some small image processing thing. There's like a compilation job for like GCC compiling a file. Like its trace is taken from like pieces of those applications, right? Or like there's a solver, right? Like a Go solver or something. I don't know whoever's familiar with it. But yeah, anyway, so it's like a combination of like 30 or so of these different workloads that are chosen to sort of be representative of like compute jobs on a computer. Yeah. One of the benefits of doing that kind of thing is that everybody's evaluating with the same set of benchmarks, so you sort of start learning, like, this is the characteristic of this benchmark, and so by looking at an idea, I can see whether it's reasonable based on my understanding of these workloads. Whereas if I create my own workload, I'm like, oh, here's PowerPoint changing from one slide to the next, and I evaluate on that. It's hard for me to have any intuition about that unless you tell me a lot about the workload itself. So, yeah, I don't know, it's kind of a trade-off between all these things. Yeah. Okay. So the next thing I want to ask is retention profiling now sort of a solved problem? And how important is this retention error profiling going forward? Right. So the high level motivation for these questions is like, should we continue focusing on this problem, or is this essentially good enough? Right. What are your thoughts on that? So one thing to note about going forward is, I don't know how many of you took Professor Mutlu's lectures, but he's talked a lot about like technology scaling going forward, right? And so as we try and make these Oh, is that the end of the lecture? Yeah. Okay, so fair enough. Okay, I don't want to keep you after that. So I think I'll put these slides online. There's just these couple extra discussion questions, and next week, so we'll get started with, I guess, your guys' presentations. So yeah, very good. Yeah. All right, thank you.